Mechanics Block 1 course. We have basic concepts of statistical mechanics. The structure of this it consists of 4 units. First unit is basically an introduction unit. Here we will deal with the basic terminologies, that is elementary probability, probability theory, permutations, combinations, random variables, just like binomial theorems. Then we'll focus on description of a system in equilibrium and phase space, macro state and micro state. In this unit, let me start with what statistical mechanics is. In UG syllabus, we have read thermodynamics. So, in thermodynamics, we deal with macroscopic systems. But here, the difference is we have a collection of large number of systems and we'll study their properties. You have idea about thermodynamical variables, and we will read the properties of those thermodynamic variables considering the probability of those systems. We will explain the thermodynamic probability, phase space, and we have some basic terminologies. For example, we will read about your toss of a coin, then what is the probability of head and tail? One can tell if we have two coins, then simultaneously we can tell head. We have head and tail and head, and tail and tail. So the sample space of two coins can be represented by four things. Four things, that is S is equal to HH, HT, TH, TT. Now we can have a sample point. Suppose S is the sample, A is the sample point, then you can say A is a subset of S. That means if you consider one of the sample point HH, HT, TH and TT, if you consider one, that is A, so A is a subset of S. Similarly, we can define events. What are events? And that means if you throw a coin, toss a coin, then we can say we are performing some events. Then in that case, we will discuss what is independent events and what is mutually exclusive events. Events which are independent when the actual happening of one outcome does not affect the probability of the outcome. Remember, what are independent events? Independent events are those when one outcome of the event does not affect the probability of outcome of the other. For example, if you toss two coins, if the first coin gives a head, the second coin still has equal probability. The outcome might be head or tail. If an event can occur in M ways, suppose there are M ways, another event can occur in N ways, then total number of occurrence of the event is M into N ways. M multiplied by N. Head M times, tail say N times, Total occurring will be m into n times. Then mutually exclusive events. Events can be mutually exclusive when one outcome exclude the probability of another event happening. So, for example, if a coin toss, we get either head or tail, but not both simultaneously. So, event A can occur n times with n mutually exclusive events. Then what is probability of A? That is number of times, number of outcomes, that is small na, divided by total number of outcomes. So you can see this one, that probability of an event, you can see this one, the probability of an event is n minus n, this one, n minus n by n, which is equal to 1 minus PA. Note that probability of A plus probability of B is 1, means 100%, which means the sum of probabilities of an event occurring and not occurring is unit. Then conditional probability, the probability of an event A happening when an event B has already happened. It is usually denoted mathematically by PAB. You can find P within probability of A oblique B is probability of A intersection B divided by probability of B. So probability of A intersection B denotes probability of A and B. This is called intersection. Now we have some general rules of probability. Then what are they? Probabilities are additive in nature. Probabilities are additive in nature. Probability of A union B is probability of A plus probability of B. Probabilities are multiplicative in nature. That is, probability of A into B is the probability of A into probability of B. Probabilities can be normalized to unit. Then so there is one problem you can say. Suppose we have a die of 6 face. What is the outcome of 3 or 4? So probability of 3 or 4 means A is equal to 3, B is equal to 4. Then probability of 3 or 4, probability of 3 will be 1 by 6 because there are 6 faces of a die. And probability of B is also 1 by 6. So probability of 3 or 4 is probability of, that is 1 by 6 plus 1 by 6, 1 by 3 each. Then we will focus on permutation and combination. We have read in our plus 2 stage what is permutation and combination. Permutation specially represents an arrangement of number of distinguishable objects. That means, how can, suppose there are 3 objects or 3 persons A, B, C. So there are possibly 2 chairs, 3 persons A, B, C, and we have choice 2 chairs. So how can they be seated? Either A, B person can sit at a time, or A, C can sit, or B, C can sit, or C, A can sit, or C, B can sit. In this manner, we have 6 ways, 6 possible ways. So the number of permutation of n objects, say bold n objects, taken small n times, then can be written as probability NPN. These types, probability of NPN can be written as n factorial n minus n factorial. That means it is denoted by NPN. Similarly, combination is written as NCN. Probability is NPN, combination is NCN. What is the difference between permutation and combination? Permutation, that is NPN, is bold N factorial by small n, bold N minus small n factorial. What is combination formula? Bold N factorial by bold N minus small n factorial, along with in the denominator there is small n factorial. So this is the difference. Bold N factorial by bold N minus small n factorial divided by that is probability. If you divide another or multiply the denominator with small n factorial, then this becomes a combination one. Now we will focus on random variables. What are random variables? If you consider the random variables distribution, suppose we have a table. What is the probability of dice? Here, the probability of 1, 2, 3, 4, 5, 6. First probability is you have 1 and a 1. Second probability, 2 dice. First probability 1, 1, 1. Second probability 1, 2 and 2, 1. Third probability 1, 2, 1, 1 and 2, 2. Next probability 1, 4, 4, 1, 2, 3 and 3, 2. Next probability 1, 5, 5, 1. In this manner, if you justify, you can find the probability distribution occurring randomly. So this is the variables which occurs here, that is 1, 2, 3, 4, 5 and 6. Those variables are random variables. And randomly you can calculate the probability. Throw a dice. What is this? 2 dice. 1, 1 may be probability, 1, 2 may be probability, 1, 3 may be probability, 3, 1 may be probability, in this manner. So you can take randomly the probability of throwing 2 dice at a time, and this is called the variables we choose 1 to 6 are random variables. Similarly, in statistical, why you will discuss this one? If you say x1, x2, xn in statistical mechanics, we consider large number of systems. Okay, when you consider large number of systems, we must at a time we cannot study the properties of a system. We have to consider the probability of a system, which is our required one. So in that context, the required probability must consider your variable one, that is a random variable, a randomly chosen variable one. Then you have idea about phase space, and this phase space describes a system in equilibrium. What happens in thermodynamics? We have read various types of equilibrium: thermal equilibrium, mechanical equilibrium, chemical equilibrium, thermodynamical equilibrium, so many types of equilibriums. So in statistical mechanics, when you study the properties of certain systems and compare them, or we mix them, or we subtract them, the two systems must attain equilibrium. That is the basic property. So equilibrium condition should be maintained while considering large number of systems into account. For this, the first thing is we must know the phase space and phase volume. You have read in classical mechanics, in the phase diagram, suppose a point is represented by x, position coordinate x, and momentum coordinate vx. Then this is called your phase space. The diagram you show here, this diagram you show is your phase space diagram. This is momentum in y-axis, px, and this is x. This point is phase point, pxp, and this is phase diagram. And what will be the volume in that case? Suppose we have a change in x, delta x, change in y, delta y, change in z-axis, delta z, and corresponding momentum changes are delta px, delta py, and delta pz. Then phase space volume will be dxq into dpq. That means delta x into delta y into delta z multiplied by delta Px, delta Py, delta Pz, that is called the volume in case of phase space. Then we will consider what are macroscopic states and microscopic states, or macroscopic systems and microscopic systems. While considering this, in phase space, we can suggest a system can be divided into very small elements or cells or volume. That is gamma space. Phase space is otherwise known as gamma space, where you can say in classical mechanics you have read that in a generalized coordinate system, Q and P, while considering the Lagrangian or Hamiltonian of a system, you have considered Qn, Q3n, that is delta Q1, delta Q2 up to delta Q3n, delta P1, delta P2, delta P3n. So this is sum over continuous product of 3n objects. This one you can find sum of continuous product of 3n objects, sum of continuous product delta Qi into delta Pi. And in a two-dimensional phase space, we can imagine it can be considered large number of similar cells. And each cell has del dpq into dq. The volume of a small cell. We have large a system, we can subdivide it into large number of cells. And we can represent them as macroscopic state or microscopic state. A macro state, you can say this specification where the various cells lies in one system, a large number of systems, we can say it is a macro state. If it is quite, one example is very simple. Suppose with an example, there are 3 cells in phase space labeled as 1, 2, and 3. So the 2 particles A and B enumerate the different macro state and the micro state corresponding to them. So these are cells 1, 2, and 3. So number of possible arrangements are this. AB, you can have arrangement AB or 0, or you can have A or B or B or A. In this manner, you can choose different number of cells. That means you have a system, you can divide into, suppose 3 cells, you have 3 rows and a number of subsystems you can define. So when you consider a cell contains a large number of states, it is considered to be macro state, or if it is contains very less, it can be treated as micro state. And for a many body system, you can choose, suppose there are momenta is P1, P2, P3, and Pn, and corresponding coordinate system, generalized coordinate system, you have read as in Hamiltonian. So you can consider that Hamiltonian del Q by del T, classical mechanics re padha jaiche, that is del H by del Pi. And del Pi by del T is minus del H. H is a function of PQ, this one. So this forms a 2 first order differential equations. And the corresponding differential equation, you have Newtonian equation of motion, gives rise to mass multiplied by your displacement. This is your multiplied by this acceleration term, m d square qi by dt square, m is del uq by del qi. Del uq divided by del qi. So you can choose this. And here the Hamiltonian of this function is p square by 2m plus uq, and correspondingly you can have a determinism or causality in classical mechanics. In classical mechanics, the phase space is, or ergodic space, is a combination of phase points or 3n phase points. But here in classical mechanics, when you consider a large number of systems, you have to summarize them. And while considering such type of systems, we must deal with the probability of the system. If we consider the probability of the system, then it will be very easier on our part to consider the total probability. And another major variable, that is thermodynamic variable, that comes across, that is known as entropy. The entropy of the system represents the total probability of the system. So while considering this entropy, this is most important variable which determines the statistical, or which governs the statistical mechanics. So the first one is, in this chapter, in this unit 2, we will discuss continuous probability, some limit theorem, Poisson's distribution, binomial distribution, some regards to the binomial distribution. We will also discuss what is the discrete probability distribution. As a discrete probability distribution, when we start, then automatically binomial distribution, Gaussian distribution, characteristics functions will be discussed. Then we will correlate entropy and probability of the system. So in unit 2, the major requirement is, how can we define entropy? How can we correlate entropy with probability, thermodynamic probability, besides especially omega? So first thing is, we must note what is the discrete probability. Discrete probability, we have discussed random variables and continuous discrete random variables, as well as continuous random variables. These are two parts of random variables. What they did, they suggest for a description of a system, these two variables are bare necessary. Now, we have certain distribution formulas which will govern the statistical mechanical equations. Say binomial distribution or Gaussian distribution, whatever may be. Suppose if you consider binomial distribution, suppose P is the probability of an event A. And A is the outcome of some experiment. Similarly, Q is the probability of event A and not happening in other words. If A and B are two possible outcomes, and P is the probability of outcome A and Q is the probability of outcome B, so under normalization condition, P plus Q must be 1. Or one can say Q is equal to 1 minus P. You can see this one. What is occurring of P here? P can occur n times and Q can also occur n times. This P occurs n times, Q occurs n times. So the probability of n such events can be written as PPP QQQ, that is n times P, n times Q, P to the power n, Q to the power n. But what is this P to the power n? Suppose Q occurs R times, this will be Q to the power R. Such that n plus R is equal to Q, bold n, and R can be written as bold n minus n. Hence, the probability of such event is n factorial by n factorial into R factorial P to the power n. q to the power n minus n, which can also be written as n factorial by small n factorial, and this r factorial is n minus n factorial, p to the power n, q to the power n minus n. So the order of the arrangement is important. Hence, the coefficient NCN Pn is known as probability mass function, PMF. This is most important one. Pn is known as this Pn, which is NCN p to the power n, q to the power n minus 1, and Pn, this factor, this represents your continuous probability of this system and probability mass function. Probability mass function plays a vital role while considering this one. Suppose we have 6 fair coins, so probability of getting 4 is 0.23%. Probability of obtaining this 4 is only 0.23%. When you consider some binomial distribution, we must know what are moments of binomial distribution. Suppose we have a variable x1, x. Then what are probability of possible distinct events? That is x1, x2 up to xn. So the mean value, the average value, you know that will be n times. X1 will occur n1 times, x2 will occur n2 times, and xn will occur nn times. So n1 x1 plus n2 x2 plus nn xn by n. So expectation value of x is nn xn by n, which is equal to Pn xn. Now fx is any function of x. The mean value or the ensemble average of the function can be written as Pn gnx. What is gn? Gn represents a function. Fx is a function of x. Then we can represent gn is another function of x. So the expectation value, that is gx, can be written as Pn gx. So if we have two values, that is f plus g, can be written as Pn f plus g. Fx is a function, gx is another function. By property of addition of probability, you can find f plus g, which is Pn f plus g. That is Pn fx plus Pn gx. Similarly, multiplication, that is probability of average of f multiplication of g, that is f probability multiplied by g probability. Similarly, if you multiply, as you have read in case of linear property of a function, if you multiply the probability function with a number, say c fx probability, that will be c will be outside, then probability of your fx. In this manner, you can calculate large number of systems probability. Suppose if x, not only the function of x, we can consider another variable, that is y. X is a variable, fx is its function. y1, y2, y3 are random variables. gy is a function. In that case, fx and gx are two similar functions, homogeneous functions. But we have heterogeneous functions, fx and gy. Fx is a function of x variables, gy is a function of y variables. Then also you can calculate the probability in terms of this mass function, that is fx into gy, can be written as the average of fx into gy is Pn fx, this one, Pn fx into Pf gx, this one. So one can, this line, this is important, or fx into gy average is the average of fx multiplied by average of gx. So finally, you have a relation that is that can be taken as the deviation. What is the deviation? Deviation in statistical mechanics is defined by, suppose x and x probability. So what is the deviation? X and x average. x minus x average ର whole square is the deviation ର square delta x square. So delta x is the actual value, x average is the probability value. So what is the deviation you have obtained? That is x minus x average ର whole square is deviation delta x ର whole square. Or in our formula we can write delta x square as small sigma square, which is Pn x minus x average ର whole square. Now, if all the possible outcomes we consider x or y or z, then we can calculate the total deviation as sum of sigma summation n Pn x minus x factor x average ର whole square. In this manner, we have large number of distribution functions. So we conclude here that we have n relative standard deviations. Then we can find moment of by binomial distribution function. We can find moment of each function. Similarly, we have continuous distribution. When distribution is continuous, when discrete random variables are discrete, randomly taken, we binomial distribution. But when it is continuous, we will apply Poisson's distribution. And Poisson's distribution is a discrete probability distribution that expresses the probability of given number of events occurring in fixed interval of time or in space, either in time or in space. So we can represent this deviation by this formula p xk. This is p xk is equal to lambda to the power k g lambda k factorial. Lambda to the power k g lambda k factorial. This is lambda to the power k e to the power minus lambda by k factorial. Lambda is the mean events per interval. K is the actual number of events. Now we can define the Poisson's distribution by this formula. That is, Poisson's distribution can be written by this formula, last one, that is px e to the power minus lambda, lambda to the power x by x factorial. So when we consider this is the Poisson's distribution formula, remember Poisson's distribution formula or the probability of mass function can be written as px is e to the power minus lambda, lambda to the power x by x factorial. Now we can consider the sum of probabilities of the system, which is the condition of normalizability. What is that one? Summation x is 0 to infinity px is e to the power minus lambda, lambda to the power x by x factorial. And in turn it will be unit. Total probability will be unit. This is about Poisson's distribution. Then, like moment of binomial distribution, we have a moment of Poisson's distribution. So we have to calculate, moment means here we have to calculate the mean and variance of Poisson's distribution. Mean means x, then we have to calculate mean variable is x, written as x expectation or x average, that is summation x is 0 to infinity x px. So when we will distribute this one, it proves the x expectation is lambda e to the power minus lambda summation lambda to the power x minus 1 by x minus x expectation. And ultimately average value of x will be lambda, and lambda is a parameter of mean distribution. So what will be the variance delta x? That is sigma square. The variance in Poisson's distribution can be computed. Remember these formulas. variance in compute distribution can be written as sigma square is the expectation of average of x minus x average whole square. That was what was sigma square in binomial distribution, that was x minus x average whole square or delta x square. But here it is average of x minus x average whole square. This is the difference between binomial distribution variance and Poisson's distribution variance. And remember the total variance sigma square, in that case it was 1, but here it will be lambda. Hence, the standard deviation of Poisson's distribution is root over lambda. Then we have continuous probability distribution. Suppose we have a number of n, we have a number n, and that means the binomial distribution has factorials of some number n. So, under such circumstances, if we consider n is very large and we have variables x which ranges from an angle x which changes from 0 to 2 pi. In that condition, the probability, the outcome of exact within 360° 2 pi rotation, the probability is written as 1 by 360. So in that case, the probability of outcome gives exact value which tends to be approximately 0. That means P divided by infinite probabilities are possible. When probabilities are infinite outcomes are possible, then probability will be 1 by infinity, that will be 0. Under that case, to overcome such a situation, we focus attention on some intervals. Let us consider the variables starts from x, and after interval x plus dx, we will consider the calculation. We will start the calculation. And at that point, we define a probability density function, that is PDF, probability density function, that is rho x, or you can say rho x or small px, some books have taken, is equal to dpx divided by dx. So in that case, we can consider the probability density function by this equation. Px is integration q1 to q2 px dx. Remember, if all the values of x are equally likely, the probability of finding x in the interval a1 and a2 can be written as px is a1 to e2. In the interval probability density function, px, some books have written rho x into dx. And S, if we consider S represents sample space, this factor is S. A1 to A2 px dx, this factor is x. As a result, we can find px dx is 1. So the LHS of this equation gives probability of some variable, and RHS is normalized to 1. Next one is moments of continuous distribution function. Suppose x is a continuous distribution function, then the expectation of x can be written as integration over s, x we can find the moments of continuous probability function. So if you consider the continuous distribution function, then its nth probability is written as average of x minus x factorial to the power n is integration minus infinity to plus infinity x minus x average to the power n into probability distribution function rho x into dx. This is about Poisson's distribution function. Then we have Gaussian distribution function. You have read Gaussian distribution function in your +3 stage. Gaussian distribution function is an exponential function. Normally, e to the power minus x, this is Gaussian curve, this curve moves to top from a peak it returns. This function plays a very vital role. You all have read what is a Gaussian function. So, the distribution function, Gaussian distribution function, you might know rho x is equal to 1 by root 2 pi sigma square e to the power delta x square. Here there will be variance by 2 sigma square. That means this one is your Gaussian distribution function, that is rho x, or can be written as Gaussian distribution 1 by root 2 over 2 pi sigma square e to the power minus delta x square divided by 2 sigma square, while delta x is x minus x expectation square. Our sigma square is a variance term, and a 1 by 2 pi epsilon 1 by 2 pi sigma square is a normalization constant. Okay, so this gives your function, this rho x or small px can be 1 by sigma into root over 2 pi exponential of x minus, if we consider expectation of x is minus mu, this is x minus mu rho whole square by 2 sigma square. So px is 1 by sigma into root over 2 pi exponential of x square by 2 sigma square. This shows Gaussian distribution. The width of the Gaussian distribution is given by 2 sigma. So it clearly shows the Gaussian distribution function have a mean variable x is given by x px into dx. That will be, if you put the value of px from Gaussian function, that will be, what is your Gaussian function? Px is 1 by 2 pi sigma square exponential minus x minus x expectation whole square by 2 sigma square you put, that will be, this will show that expectation of x is equal to your mu. It is obvious that the RHS gives a mu. This mu is very important. Okay, and we can say the total expectation value, total average value tends to unit if you use Gaussian distribution function. We have read binomial functions, we have read Poisson's distribution functions, we have read Gaussian functions. Another function is characteristics function. Characteristics function is denoted by rho bar k or p bar k, some books have written. The characteristic function, remember, is the generator of moments of the distribution. You have read generators in classical mechanics. Classical mechanics re charta generators padhithilo, q dot p t, p dot t, q p t, p q t, so many 4 generators. Similarly, here characteristic function is the generator of moments of distribution, and we will use the Fourier transform to represent the probability of the function. So the nth moment is represented by this one, the nth moment, the characteristic function nth moment, xn is minus infinity to infinity, xn px dx. Now this is our characteristics function. This is pk is e to the power minus ikx, e to the power minus ikx into dk. This is our characteristics function. From Taylor's expansion, e to the power ix is ix to the power n by n factorial, or e to the power minus ix is minus ix to the power n by n factorial. E to the power minus ikx is equal to minus ik to the power n by n factorial into x to the power n. Therefore, the moments of distribution are obtained by expanding P bar K in powers of K. তাহলে P bar K is equal to minus IK to the power N, this one, minus IK to the power N by N factorial into X to the power N, minus IK to the power N by N factorial. So moments of the probability distribution function around any point mu can be written as e to the power ik mu pk, e to the power ik x minus mu. We have considered mu can be a distribution function. We have considering around a point mu. Then this will be minus ik to the power n by n factorial into x minus mu to the power n. Now to extract the nth moment, we simply take nth derivative, that is x to the power n is del n, nth derivative, that is del n by del minus ik to the power n pk at k is equal to 0. So we can obtain the nth moment of the variables. Remember, in this characteristics function, we can take the derivative depending on the nature of the problem. It is important to note that the two methods should given the same moment. However, if n is large, we will prefer the derivative method. Remember, when we will consider the derivative of the function, now we can consider the derivative of the function when it is large. Then you have cumulant generating function. What is cumulant generating function? Cumulant of a probability distribution are set of quantities derived from logarithmic of characteristics function. When you consider the logarithmic of the characteristics function, it provides an alternative representation. Alternative representation, that is rho k is rho k is equal to minus ik to the power n by n factorial into x to the power n. So rho bar k can be written as by an expansion, normal expansion. If you consider the logarithmic of that function, then that will be a cumulant generating function, that is pk bar is 1 plus minus ik x factorial minus ik square by 2 factorial x expectation square plus minus ik to the power q by 3 factorial into x expectation q plus so on. So ln rho bar k is equal to 0. The logarithmic characteristics function may be rewritten as ln pk is minus ik to the power n by n factorial x to the power n. So ln pk is minus ik expectation value of this plus so on by 2 rho factorial and so on. In these terms, x, this one, we have written another term e. You can find here x expectation c, x square expectation c. When c number is there, it is called cumulating functions. The logarithmic characteristics function can be treated as cumulating functions. And we finally, the Gaussian distribution function that you have read, that is px is equal to sigma into root over 2 pi sigma x minus mu about point mu x minus mu square by 2 sigma square. This can be correlated, and we obtain that a cumulant function of x, suppose cumulant function of x can be mu, and a x square, cumulant function of x square can be sigma square.
Sir.
In this condition, we can find the some
Sir.
theorem which can relate this one. First one is central limit theorem. What is central limit theorem? let us consider any system
Sir,
with
I have
any distribution function. What happened,
actually, sir,
Shivani?
yes, sir. Actually, sir, I did not get the books yet. So if you share the screen, then I can understand well.
No, no, you should get the book. Well, it is your duty. Okay. Then let us consider
Page.
a system with any distribution function. Then we have two random variables, say x and y. What is central limit theorem? Consider any system with any distribution function such as binomial, Gaussian, Poisson or Lorentz distribution function. The central limit theorem states when a sufficiently large number of similar systems are sampled, remember, we have similar systems. If you take sample those systems, the resultant distribution is always a Gaussian distribution. Remember, if we have large number of systems, similar systems, and we are sampling those systems, then we are sampling those systems, then we can consider the Gaussian distribution. The resultant distribution will be Gaussian distribution. What is central limit theorem? Once and again, we have large number of similar systems when sampled, then the resultant distribution will be Gaussian distribution. This is the statement of central limit theorem. Or in other words, we can say, if we analyze this, when a probability distribution is sampled for large n, the average of the sample converges to Gaussian distribution. The proposition is known as central limit theorem. This proposition is called central limit theorem. Mathematically, we can say, suppose we have a characteristics function phi, which is a function of k. Then what mathematically we can say, this is phi k, which is this one. Phi k will be e to the power ikz integration, surface integration, integration over x and integration over variable y, where x can change some interval x to x plus delta x and y can change to y to delta y, and z can also change from z to delta z, but characteristics function integration is within the two, that is e to the power ikz rho x, or p is a function of x, q is a function of y, dx dy. Then when we consider same large number of systems and we consider Gaussian functions, in that case we can devise that z, another variable, that is characteristics function phi k, can be written as expectation or average of e to the power minus ikz, which is integration of the individuals, that is rho k bar into q k bar. So in that case, we can simple produce the characteristics functions as a limit of Gaussian functions. That is the statement of our central limit theorem. Then derivation. How can we derive central limit theorem? That is most important one. We can derive central limit theorem by considering n variables, say x1, x2 up to xn, and compute the mean of the sum. That is, s is x1 plus x2 plus xn divided by n. So in essence, we must show that the sum s, which is a function of s, is 1 by root over 2 pi sigma square into e to the power minus s minus x expectation square divided by 2 sigma square, which is a function of s. what we have told, phi s is the probability of density function, where sigma s square is the variance of distribution. So let phi k is a cumulant generator for S. Therefore, we get phi bar k is e to the power I k bar, which is integration over x1, integration over x2, up to integration over xn. This one, that is integration over x1, integration over x2, and for large number of n, integration over xn, e to the power minus ikx, px1, px2, pxn, up to this one. Then we can say this phi k, the phi k can be written as, you can derive and find phi k is equal to rho k by n rho wholes to the power n. So we can say, we can evaluate this one by considering the functions, which are which are very neglecting the higher terms. Higher terms only we consider second up to second term. The third and fourth term of 1 by n variables are not taken into consideration. Then we can find these functions. Probability of the density function phi s is equal to 1 by 2 pi integration k is equal to minus infinity to plus infinity and minus infinity to plus infinity e to the power minus ik plus ik whole square by 2n x expectation square into e to the power ikx into dk. So phi s is 1 by 2 pi e to the power minus ik x expectation minus s. So in this manner, when we proceed, we find the probability density function of a large n when n is much greater than s corresponds to a Gaussian function. That varies phi s is 1 by root 2 over 2 pi x square average divided by n into e to the power minus x average minus a square by 2 into x square by n. Now this is yes, which is the normal distribution function, gives a Gaussian distribution function. This is the central limit theorem and that can be derived. Now we can define a term entropy. We have read in your graduation that entropy is the disorderness of a system. S is equal to k ln omega, and omega is the thermodynamic probability of the system. So how this entropy is related to probability? In order to read that, the quantity we have defined, yes, can be taken as the disorderness of the system, or you can say that is the entropy of the system. And you have read the third law of thermodynamics, which is related to entropy in your graduation stage. Entropy represents this disorderness. If we have number of systems, then we can say the number of systems can be, the disorderness lying in that system can be converted by this equation S is equal to ln omega. And by approximation, if we use Starling's approximation, that is log n factorial will be n log n minus n, which is n factorial. If you proceed in that, you can define a term thermodynamic probability, that is omega, this one. This omega is n factorial by sum over continuous product of 6 variables, say I is 1 to 6, one example, ni factorial, that will be n by e to the power n, sum over continuous product I is 1 to 6, ni divided by e to the power n. You have divided e to the power n in the numerator and in the denominator, then you can find the logarithmic of that. When you find the logarithm, you will define the quantity entropy, that is S. S is equal to K minus N sum over I, Pi log Pi. This is called Shannon form of entropy. But there are normal forms of entropy. S is equal to K ln omega. So entropy not only represents the disorderness of the system, it indicates how the entropy is related with probability. If P is probability, rho is probability, then S is by KB, say K beta or some constant K you can simply say is minus N times N is a large number of systems, probability Pi times log of Pi. This is the relation between entropy and probability. Then you can go to, when you read entropy, you can go to third unit. Go to third unit, unit 3. Unit 3 represents the sorry, taking a lot of time. Wait 1 minute. That is your statistical relation between statistical mechanics and thermodynamics. Here you have read Lagrange's maximization, Lagrange's multiplier problem. You have considered a problem lambda to solve the differential equations. Then we will define a Lagrange's multiplier lambda, and that will indicate entropy maximization. Then we say how statistical mechanics and thermodynamics are related by Boltzmann's constant. Then we will show Maxwell-Boltzmann distribution function, discuss the principle of equal a priority probabilities. So at first, tomorrow I will share the screen because of their wrong interpretations. It is difficult to take some time. So what is entropy maximization? Let us first focus when you define a Lagrange multiplier. Lagrange multiplier means when some differential equation is not solved, we define lambda times something and we find the value of lambda. As a result, we solve the differential equation. So, this Lagrange multiplier method is used for constant optimum maximization. And that method is like this. Suppose we have we can maximize a function which is, or we can minimize a function. Suppose we want to maximize a function f which is function of x1, x2, xn subject to equal constraints given as g x1, x2, xn. Now we introduce a Lagrange multiplier lambda. Here in your book you have taken a lambda j. That means Lagrangian, which is a function of x1, x2, xn, you can find this one. Lagrangian, which is a function of x1, x2 and x1, this line, and lambda 1, lambda 2, lambda n can be written as f of x1, f2, xn, sum over j is 1 to n, lambda j, gj, x1, x2, xn. Till the critical point are found for solving this equation is del L by del xi must be 0 and del L by del lambda I is equal to 0. When you solve such systems, we get these equations that del L by del x must be equal to del F by del x minus lambda del G by del x. Similarly, del L by del y is del F by del y minus lambda times del G by del y. That means del L by del lambda is equal to gxy, which is basically 0. So this lambda is the Lagrange's multiplier, and this method is used to obtain maximum entropy distribution. This was taught in your +3 first year courses and in PG mathematical physics syllabus also. So we consider some discrete distribution where we can represent the relation. Let us consider there are a die with k faces. Okay, we have a die having k faces. So the properties of probability of normalization condition may be written as summation I is 1 to k pi, which is net probability is 1, which is equal to sum of probability. That means if net probability is 1, then a sum of probabilities minus 1 must be equal to 0. Then we define summation I is equal to 1 to k total probability minus 1, which is 0. Let it be a function of g times a characteristics function or a constant, you can say, that is g, which is pi. Similarly, we consider a multivariable function, a function of p1, p2 up to pk. Then we define the relation f of pi is x by nkb. Here, this equation s by nkb, which is equal to summation I is 1 to k pi ln pi. In this way, if we proceed, we have to use the Lagrange's maximization property, that is L is equal to Lagrangian can be written as f is a function of pi minus lambda times g is a function of pi. For simplicity, we take a specific variable, one variable, say jth variable. When you consider the jth variable, then we calculate the partial derivatives and we calculate the value of lambda. And the value of lambda for specific variables when calculated and we normalize that one, then we find the value of normalization constant A such that A is equal to summation I is 1 to k pi and A is a normalization constant. So this Pj can be written as e to the power minus lambda minus 1 divided by A. And this, if you have a dice, you can find the probability of one number is 1 by, if it has 6 faces, then the probability of finding a jth face is 1 by k times, or in case of dice, it is 1 by 6 times. So we can say the after normalization condition, the constant we have defined GPI, that is equal to summation I is 1 to k pi minus 1 will be 0. When you consider the average of that number, we find the Lagrangian can be written by some another constant, that is lambda, initially written as Lagrangian was f is a function of pi minus Lagrangian multiplier lambda times gpi, where gpi represent a constant. Now we define this as beta h times pi, where this beta is another constant. This h times pi is another constant and beta is another Lagrangian multiplier. Why this two Lagrangian multipliers are necessary? Now it should be in your mind, one Lagrangian multiplier is possible, but due to large number of systems, the averaging those systems will never give a correct value with a single multiplier. That's why we have considered two Lagrangian multipliers. And on the optimization condition, when we consider, we calculate a number that is called partition function. That is the building block of statistical mechanics. That is Maxwell's distribution function. You will see that the partition function is in statistical mechanics is represented by a term Z. And the Lagrangian multiplier, it is related to the second Lagrangian multiplier. One was your lambda, another one was beta. So for j number of jth item, jth variable, z is equal to summation j is equal to 1 to k e to the power minus beta epsilon j, where epsilon is a very small number. So remember, this partition function is this one. Z is equal to j summation 1 to k e to the power minus beta epsilon j. And you will be able to see in Maxwell distribution function, when we will discuss, it plays, this partition function plays a vital role. Now, this is for discrete distribution. If the distribution is continuous, that means in place of summation, we can find entropy maximization here. And the entropy maximization condition, indicates the temperature is basically, we have equipartition theorems, that is energy is equally divided among all the degrees of freedom. And to study the possible velocity distribution function, we have a probability density function rho v, where v represents the velocity of the random variable. Now we consider fv, any random variable, fv is equal to s, which is integration rho v log rho v dv. So using the normalization condition, gv can be written as integration rho v dv minus 1 is equal to 0. And we know equipartition theorem, energy, kinetic energy, average of kinetic energy is half k beta t. That means energy is equally divided among all the degrees of freedom, and each degree of freedom takes an energy half kt. So half mv square average is equal to half k beta t. Therefore, we define another constraint using equipartition theorem. We define another constraint, remember, as we have defined the constraints g and h in a previous section. We define a constraint h which is a function of v. In that case, that was a function of position x in case of discrete variables. Here we define h is which is a function of v, integration minus infinity to plus infinity. This one, this constraint, half mv square rho v dv minus half k beta t is 0. Using these two constraints, gv and hv, the Lagrangian may be written as Lagrangian is fv minus lambda gv minus beta hv. Remember, we have also defined this function in discrete cases. So Lagrangian can be written as v, this is v is equal to minus infinity to plus infinity rho v log rho v dv minus lambda rho v dv. So using the optimization conditions, we can use this optimization condition, that is 1 plus log rho v plus lambda plus beta mv square by 2 is equal to 0. And rho v is e to the power 1 minus lambda into e to the power minus beta mv square by 2. So the probability distribution which come across indicates the normalization condition, that is a must be equal to integration minus infinity to infinity rho v dv. Implies a e to the power 1 minus lambda minus infinity to infinity e to the power minus beta mv square by 2 into dv. Using the result of standard Gaussian distribution, we can write a e to the power 1 minus lambda integration into root over of 2 pi by beta m. Therefore, the normalization probability density function can be written as rho v, which is e to the power minus 1, e to the power minus 1 minus lambda, e to the power minus beta mv square by 2 by a. Then rho v is equal to m by 2 pi k beta t into e to the power mv square by k beta t. So beta is equal to, this equation is called Maxwell-Boltzmann distribution function of velocity. Rho v is root 2 over m by 2 pi k beta t e to the power minus mv square by 2 beta t. Beta is equal to k beta t, that is equal to Maxwell-Boltzmann function. And this Maxwell-Boltzmann distribution of velocity is one dimension and describes, this is velocity phase space. You can find the velocity phase space. That means we have defined this is a three-dimensional picture of velocities Vx, Vy, and Vz. This velocity phase space indicates that the three-dimensional system rho v is m divided by 2 pi k beta t to the power 3 by 2 into e to the power minus mv square by e to the power 2 k beta t. To complete our analysis, we find as in phase space, what is the volume of phase space? dx, d delta x, delta y, delta z, dpx, dpy, dpz. Then the volume dvx, here v is not volume, dvx, dvy, dvz in velocity space, then v square is equal to vx square plus vy square plus vz square. If you consider this to be the radius v, then total can obtain, then total volume will be 4 pi v square dv. So corresponding distribution functions will be P1 Vh, P2 Vy, P3 Vz multiplied by, this is in 1, multiplied by the total volume 4 pi square V square into dV. And you obtain, after obtaining this, you put those values, you obtain the Maxwell distribution function, which is important one, Maxwell-Boltzmann distribution function, or you can say classical statistical function. That is the most important equation, that is rho v dv is 4 pi m by 2 pi k beta t to the power 3 by 2 v square e to the power mv square by 2 k beta t into t. And this one clearly gives you the, expression for the relation between different distribution of velocities of a function. This Maxwell's distribution function gives you the mean value, average value, and RMS value of velocities for kinetic gas molecules. So this distribution function also indicates that how the particles in three dimension are related to each other. Now, after Maxwell distribution function is related to k beta t, you can find there is a contact between statistical mechanics and thermodynamics. What is the relation? The second law of thermodynamics states entropy of an isolated system never decreases. Entropy always remains constant for reversible process. And for irreversible process, entropy changes. Then in thermodynamical quantities, we have, in that case, the Boltzmann suggested the entropy is equal to k times ln omega. K beta is your Boltzmann's constant and omega is your thermodynamic probability function. So this formulation S is equal to k log omega indicates that entropy tends to increase when there are more microscopic states associated with higher entropy. In thermodynamic quantities like internal energy U, Helmholtz free energy function F, entropy S can be divided from measurable quantities. In statistical mechanics, the partition function plays central role in connecting microscopic and macroscopic properties. So we have defined the partition function z, which is e to the power minus beta times. The partition function helps to calculate macroscopic thermodynamic quantities. So the internal energy U, Helmholtz free energy function F, entropy S, and so on. Let us consider two physical systems. You can see. Suppose first system is characterized by number of particles n. In a Maxwell thermodynamic system, number of particles, volume, and energy of a system remains in equilibrium with other system. Suppose omega is thermodynamic probability of a microstate is function of n1 number of particles, v1 and e1. E1 is energy of the system, v1 is volume, and n1 number of particles. If n, v, e remain same of the two physical macroscopic systems and they are in thermal contact, A1 having N1 V1 E1, A2 having N2 V2 E2, when they are in thermal contact, then you can find their total energy E is equal to E1 plus E2. We have two functions, omega, which is a function of N1 V1 E1, and omega 2 is a function of N2 V2 E2. Total energy E is equal to E1 plus E2 constant. Then what is the accessible microstate for A? Now, these are the accessible microstates for A. When A1 and A2 mix each other, the energy of the second microstate E2 is total energy minus E1, or you can say total energy remain constant. Hence, you can say the probability of the microstate omega E of the system E can be written as omega E1, this is omega E1 into omega E2, omega E1 into omega 2 E2 is equal to omega 1 E1 into omega of E minus E1. Instead of E2, we are writing E minus E1, which can also be written as omega is a function of E1. This indicates, what does it indicate? For a composite system, E1 will vary until it attains a particular value or it attains an equilibrium state. So we can say an isolated physical system left to itself will proceed in such a manner that it will settle down a microstate which gives the maximum number of possible microstates. Hence, the value of E, the present value of energy, the value of maximize the microstate. So, statistical speaking, A1, A2, A3, A4 are possible macrostates for the composite system. Then we can suggest the system which have large time in a microstate, its number is maximum, hence it becomes natural to identify the state with the equilibrium state of the system. Further, if a system is in equilibrium, it is found with equal probability in each of the accessible microstate omega and vice versa. So the relation between statistical mechanics and entropy are quite inevitable by these expressions. Then it is further realized by Boltzmann and entropy relation. You know S is equal to K beta log ln W. So if you consider the partial derivative of two functions, if you consider E bar is the equilibrium energy, take partial derivative of two functions to make it maximum, then del omega 1 omega 2 by del E1 must be at E1 minus E1 is equal to E1 bar will be del omega by del E1. So we used the chain rule, and consequently you will obtain a relation that the factor 1 by omega 1 del omega by del E1 must be equal to 1 omega 2 by del omega 2 by del E2 in equilibrium condition. So for convenience, when we consider two functions having number of particles, volume and energy, N1 V1 E1, N2 V2 E2, we can define a factor beta that is del log omega by del E at constant NV, and E is equal to E bar and beta 1 is equal to beta 2. We note that the parameter beta has dimension of reciprocal of energy. You can find beta is equal to del log omega divided by del E. That means beta is inverse of energy. It indicates that the for two subsystems A1 and A2, when forms a composite system A, the condition for A to be equilibrium warrants that the parameter beta 1 and beta 2 are the individual systems A1 and A2 would be equivalent. Hence, we conclude that entropy, yes, related to energy like del S by del E is equal to 1 by T. When N and V are considering N and V to be number of particles and volume to be constant, then the statistical thermal equilibrium having parameters beta 1 and beta 2 with a subsystem temperature T1 minus T2 is equal to T, we define del S by del E is equal to 1 by T, where S is entropy of the system. And we define del S by del E at NV by del log by del E at NV is equal to 1 by beta T. Hence, delta S by delta log N is 1 by beta T, which is a constant. And it was Planck who first gives this formula that entropy is related to Boltzmann's constant along with the thermodynamic probability, that is S is equal to K beta log omega. And this Boltzmann relation highlights the probabilistic nature of entropy. This relation A is equal to K beta log omega represent the probability relation or nature of the entropy. And it suggests the statistical distribution of a microstate. The greater the number of microstate, the higher is the entropy. So the relation provides a qualitative measure of entropy, and the beta, the parameter, is 1 by K beta T. So this clearly indicates that how entropy is related with this temperature as well as thermodynamic probability. Then we have to define a Maxwell distribution function or partition function. And we will consider the postulate of equal a priori probability. Suppose we are considering a microstate. To give, and when you want to describe a microstate, in say we divide into small spaces, say mu spaces we say, and volume of the surface, if you have large number of surfaces, the volume will be HQ. Let we have consider a particle, ith particle having energy epsilon I and number of particles Ni. Then N is sum over I Ni, and U is sum over I Ni epsilon I. When we move forward, we know the postulate of equal a priori probabilities, that the thermodynamic, it suggests the thermodynamic probability omega is simple the number of ways for placing n distinguishable objects, such that there are ni objects in the first cell by n1 objects in the first cell and n2 objects in the second cell. So what are the number? This number can be written as omega is equal to n factorial, total number factorial by n1 factorial multiplied by n2 factorial. All you can say sum over continuous product n divided by sum over continuous product ni. So we consider in that manner, we use Stirling's approximation and we obtain an expression which is called A is equal to exponential alpha, that is a degeneracy parameter. Then what degeneracy parameter determine? It determines the behavior of the system which deviates from the ideal gas. So in this case, the degeneracy parameter must be much greater than 1, corresponding to the classical equation. And this equation, that is Ni is equal to e to the power minus alpha beta to the power epsilon I is equal to 1 by a times e to the power minus beta epsilon I, that indicates the your degeneracy related to degeneracy parameter A. It interprets that we have to evaluate the constants in terms of thermodynamic quantities. Initially, we started with Lagrange's multiplier for maximization of certain problems. Then this degeneracy parameter A is written as the partition function divided by the total number of particles or total number of cells. So we can define this is for a single particle or single partition function, or it is also called phase integral. The two scientists, Darwin and Fowler, they suggested this partition function for a single particle by dividing this n. And if you move in this manner and you plot a graph between your n number of particles in the ith cell versus energy, that is epsilon I minus mu by kt, this takes this shape. This is how the Maxwell-Boltzmann distribution function as a function of this mu I by epsilon, this changes. You can find it moves in this manner, and the plot shows this confirms the behavior of obtaining kinetic theory of gases. There is the distribution function indicates it approaches to zero at higher energy. More the energy, the partition function rapidly decreases and becomes zero at higher energies. Then we define thermodynamic variables. We have read pressure, temperature, volume, entropy, enthalpy, Gibbs function, Helmholtz function. They are thermodynamic variables. So entropy is a thermodynamic variable which is related with the partition function along with the internal energy. By this equation, S is equal to nk beta t log z plus u by t, where u is equal to internal energy of the system. Then this is del z by del t at v, that is del z by del beta into del beta by del t at v. And if you proceed in this manner, then finally you can equate all the partition functions. U is internal energy, Z is partition function, T is temperature, S is another thermodynamic variable. Entropy is a thermodynamic variable, internal energy is a thermodynamic variable, temperature is a thermodynamic variable related to statistical partition function, your Z. Similarly, you can find if you move Further, you can say internal energy U is related to your Boltzmann's constant and temperature along with your partition function. U is equal to n k beta t square 1 by z del z by del t at V. So you can say Helmholtz free energy function F, which is equal to U minus Ts, can be written as U minus Ts can be n k beta t into logarithm of Z. And for isothermal process where temperature remain constant, then Helmholtz free energy function and pressure are related. Pressure is minus del V by del F by del V at T, which is n k beta t by z into del z by del v. So these are the relationship among various variables, thermodynamic variables with partition functions. Then principle of equal a priori probability suggests that if we have an isolated system of large number of particles, then the macroscopic properties of the system can be obtained using statistical mechanics. First one is the system consists of large number of particles and the number is fixed. Equal a priority probability suggests that means summation I Ni is bodo n. Ni is the number of particles or cells or microstates. N is total number of particles. The total energy of the system is conserved, that is Ni epsilon I is equal to E. In a given thermodynamic system, there exists a set of accessible microstates. A system will not stay in a given microstate forever. It will continually make translation between various accessible microstates. Remember, what equal a priority suggests? Total energy, there are Ni cells, energy of each cell epsilon I, sum over this is E. So it tells a system will not stay in a given microstate forever. It will continually make transition between various accessible microstates. So equal a priori probability suggests we cannot find a system which is always in one state, which lies in one state. It lies in a state where the total number of energy is equal to the sum of number of cells and energy of each cell, and the total number of cells summation is equal to the total number of particles residing in the total number of particles gives rise to summation the total number of cells. In unit 4 we have classical statistical mechanics, where we consider the average ensembles, ergodic surface and some hypotheses. Finally, we focus on Liouville's theorem. So in here, the concept of learning is the macrostate and microstate can be correlated. Phase space, that means gamma space, and phase trajectory can be done. We can find the time average of a physical quantity. We can explain an ergodic surface, and for stationary ensemble, to suggest stationary ensemble, we will suggest Liouville's theorem. Initially, classically we know gamma space, that is phase space. That is, phase space is your momentum and a coordinate space. Here we define a mu space. Mu space is a space generated by, that is gamma space. Mu space is, that is x and px gamma space. Mu space is designed by your generalized coordinate qi and conjugate momentum coordinate of a single particle, that is pi dot. Pi dot is conjugate momentum. and gamma space is having 3n generalized coordinates and 3n generalized momenta. They are related to each other. When we consider these two cases, that is phase space and gamma space, we can find the time average and define an ensemble. Then what is if we want to measure thermodynamic quantities like pressure and temperature of a system, then we measure that in classical physics for one particles. When the particle is very large, then it becomes very difficult. We take average of that quantity. Suppose F0, for example, F0, F1, F2, F3, so on, are measurements in a time period T. Then we consider the average F is equal to 1 by T integration T0 to T0 plus T dt F of Qt Pt. And we corresponding that limit, we find the thermodynamic equilibrium, the time average of a physical quantity is written as the average of large number of systems. So when you consider time average, we define the total time from initial to final one of the all the systems considering together into account. Then this ensemble, for that we need a concept of ensemble or ensemble average. And ensemble average acts as a substitute for time average. To discuss that, we can say what is an ensemble. An ensemble is a collection of large number of systems having identical properties. You have canonical ensemble, you have micro-canonical ensemble, and you have grand canonical ensemble. Number of particles, energy volume, temperature, energy volume, chemical potential, energy and volume may be same or may not be same. So depending on that, when you consider a system and for each system is divided into large number of cells and each cells have similar properties, then we calculate their ensemble average. So we say an ensemble is the collection of accessible microstates. Remember, an ensemble is an collection of all accessible microstates in equilibrium with consistent macrostates. Then we can find the ensemble average. Again, an ensemble is the collection of all accessible microstates, all possible xi velocities, momentums of n particles or energies that is in equilibrium. And the ensemble average of the quantity, in place of time average, we consider the ensemble average of thermodynamic quantities. We correlate the relative probability with the system, and we relate the probability density function with the phase function. So we define a density function. The first one is the density function, here known as phase space density function, that is rho dash subscript ps phase space density function. Sum over continuous product dqi dpi is d3nq d3np, which represents the integration over the entire space. That is integration rho dash qpt is equal to m, and we define Another function, rho density function, phase space density function is rho dash divided by m. We can normalize the density function to 1. That is rho ps qpt is equal to 1. When we associate a fundamental volume to it, then this becomes normalized and the probability density function becomes dimensionless. So it is defined by equation 4.5, 1 by omega 0, and omega 0 corresponds to phase space volume. Omega 0 is phase space volume, that is dqp dpq or dxq into dpq rho qpt into d omega. So the phase space density function should be visualized as the probability density function. Phase space density function should be visualized as a phase space density function. And when we consider the phase space density function, we can use the normalization condition, and we find the ensemble average, f average is 1 by omega 0 integration over gamma space d omega f of qp rho qpt. In this case, if it is stationary, rho is stationary, then del rho by del 2 will be 0. Then we have Liouville's theorem, which suggests if the phase space density function rho dash rho s qpt is defined at any given point of time t, then how does it evolve with time? Or if we consider an infinite phase space volume, say de-enclosing several microstates of the system at time t, and each of the microstate evolves time, then density function rho dash qs qpt depends on 3nq coordinates, and 3np coordinates are d rho dash density phase space density function by dt is rho d rho dash density phase space density function by dt plus summation I is 1 to n del rho ps by dq qi dot plus del rho dash ps by dpi pi dot. So Liouville's theorem deals with the way of representation of the point of phase space density function which moves around gamma space. That means over this space, this figure indicates an arbitrary phase space. The rate at which number of points change, that is del by del t rho dash into this one. So we consider the velocity vector in phase space, that v is a function of q dot t p dot t. So v is equal to q1 dot q2 q2 dot q into q2 q3 and dot into so on, and we obtain the velocity which is a function of rho dash psv is del by del qi rho dash psq dot plus del by del py rho dash rho s pi dot. And in this way, when we proceed, we obtain this density, that is rho s h, the density function over phase space is summation I is equal to 3n del rho s by del q del h by del pi del minus del rho dash rho s by del pi into del h by del qi. This is called your Liouville's theorem. Liouville's theorem. And the consequence is, when time evolves from t to t dash, the phase space volume element remain unchanged. First conclusion of Liouville's theorem. Second conclusion, phase space density representative points in gamma space remain constant. That is written in this manner. In gamma space, phase space volume remains constant. A system in equilibrium represents a stationary ensemble, that is del rho by del t is 0 and rho eqh must be equal to 0. So let us summarize. We have read the, we have started with the first one, some definitions, then we define certain functions, events, we find probability functions, we define ensemble, we define various probability functions, we correlated those functions, then we define the entropy with the partition function. Finally, we are able to find their time average of those ensemble functions. Okay, anyway, let us any let us thank all of you for your patience for 2 hours. Tomorrow we will meet with block 2. Thank you.